All right, good afternoon, everybody. How's B-side so far? A lot of really interesting talks. All right, so my talk today is a little bit just about some research that I was doing recently, and I think it was some pretty interesting stuff. So I want to tell you guys what I discovered, and through doing this research, I also found a potential weakness in a security mechanism. So to get started with, this presentation is just a narrative of the research that I was doing recently. I was looking into split stacks and threading during program execution and some of the security mechanisms behind these. The main driver of this talk is something called a split stack. A split stack is an alternative to a traditional program execution stack, and I'll go into all the details in just a minute. But I really wanted to understand how split stacks work. So that formed the basis of this talk. And all right, well, a little bit about myself. You know what, doesn't matter. All right. Okay, so as I mentioned, once you understand how a stack works during execution time, you can then start plugging it with various types of attacks. And in particular, I'll just go ahead and give you the TLDR at for the whole talk here, is that a security mechanism known as a Stack Canary, which if you're not familiar with, I'll go into how they are implemented in a minute. They actually provide a fingerprint into a opaque memory space. So when you launch a program, it belongs to this giant blob of memory. Well, you can now find return addresses if you have Stack Canaries enabled, because Stack Canaries have a certain fingerprint that sticks out of the memory space. So if you're an attacker and you're scanning the system's memory, well, if they're running with the security mechanism enabled, you can find where the return addresses are. And you know that if you can compromise a return address, then you can compromise a program, or at best make the program crash. All right, so the background material. I'm sure many of you guys are familiar with stacks. Stacks, that's a stack of stacks. Okay, so I'm just going to kind of cover everything which will help paint the story about the attack. Okay, so stacks, if you're not aware, are a data structure that contain things. It just contains information in this data structure. They're used all throughout computer science, but the idea here is that there are two operations you can perform to a stack. You can push items or push data onto the top of the stack, or you can remove items from the top of the stack. There's only two operations, a push or a pop, and they only occur to the top of the stack. You cannot manipulate the middle of the stack or the bottom of the stack. As I said, this is used all throughout computer science, but what's important here are execution stacks. So an execution stack is what a program uses during runtime. So if you think about what a program does, it starts off in the main function, and then you call subsequent functions. So main calls foo calls bar, and a whole series of functions are getting executed. Well, you have to store information about that function, the local variables in the function, the return address of the function, and the parameters or the arguments passed to the function. They all belong in this temporary storage area of the process known as the execution stack. Every frame is an item that is pushed onto the top of the stack when you call a function, and when you return from the function, you pop that stack frame off, or that activation record, or whatever you want to call it. And it looks something like this. I stole this from the Wikipedia, so that's completely legit. This is two functions here. These are two separate stack frames, the blue stack frame and the green stack frame. Because you can only do things to the top of the stack, the currently executing function is that item at the top of the stack. As I said earlier, it's got the locals or the automatics, it's got the return address, and it's got the parameters that were passed to it. So this is kind of what it looks like in memory during runtime. And I've done just a little bit of disassembly here just to give you an idea of what the code actually looks like when your compiler generates stack frames. So I'm going to try to use this. I play Rock Band. I know how to use a mic. All right. Wow. Okay, so in this very simple example, all I'm trying to do is illustrate what a stack frame looks like during the actual assembly for it looks like. Because this is very useful, because this helps identify what we need to do to actually attack a running process. So I've generated a 3-function program, foo calls bar calls buzz. Now you've seen in the function bar, I've defined 2 local variables. Okay, so it just looks like that little fancy diagram there. Here is the assembly dump of that. As you can see, foo and buzz look pretty similar. This is the portion of the code that is setting up the stack here. You're pushing the stack base pointer. You're pushing a value onto the stack there. If we look at the function bar, you notice there's a subtraction here because the stack actually grows downward on an x86 machine. This is focused on x86 program execution. And that subtraction is enough memory to actually hold the local values of that were defined in the user's code. Okay. So that's just kind of what we're looking at here for a regular function without any security mechanisms in place. So all of this discussion so far has led up to just singly threaded programs. Now remember, a process has 1 stack space. That works fine for single-threaded programs, but what about multi-threaded programs? Because you have now multiple threads executing functions independently of each other in a non-deterministic way. A compiler cannot decide at compile time what functions are going to be executed in what order due to this multi-threaded problem here. So the solution is that every thread gets its own stack space. But this presents a problem because, as I said, stacks contain information. They contain, the process stack contains information about the callers and the callees of that thread. A compiler doesn't know how big to make the thread when it's building out your program, when it's making that assembly code that I just showed you. So there's a very simple solution to this. And I think it's probably not the best solution, but this is what POSIX does. They hard code the size of threads. So when you start a thread, if you do pthread create in your program, or if you're using some kind of threading library, the threads are created with a hard-coded size. That means 2 things. Either you're going to be wasting that memory if you don't actually need it all, or you might actually blow out the stack of your thread and terminate the process prematurely. And on the system that I was investigating, it was hard-coded to 8 megabytes. Now think about that for a minute. If you're spawning threads, chances are you might be doing a lot of these all over the place. Think about web servers, something like that. 8 megabytes is an awful lot of memory for every thread. Think about the overhead. This is also not a very scalable solution. Okay, so this is just your traditional POSIX thread. Now let's think about other programming languages. Let's think about the Go programming language. If you're not familiar with Go, they really boast about being this highly concurrent, we can spawn tons of threads. Well, it turns out they do a different trick. And this is what led up to the investigation of a split stack. Instead of using the traditional stacks that I just showed you, Go uses a concept called a split stack. And what that does is it solves this hard-coded problem. In the function prologue, wrong way. In the function prologue, so the very beginning of the function of a Go program, right here is where they're doing all the stack stuff. So where all the stack initialization goes on for that function, Go makes a check. Go says, okay, I might be running on a thread. How big is the stack area of my thread? If it's too big, then what happens, if it's not large enough to hold that next function that's getting ready to be executed, Go's runtime will actually allocate dynamically a brand new stack just to run that function. So this solves the 8 megabyte problem or the hard-coded thread size problem by allocating only when it needs to. This also means Go can use really tiny threads, so they can do this in a much more efficient manner. So I've just kind of outlined what happens during a split stack, and I'll share the slides later. I don't want to blast you with fun words. But it turns out that when you actually create a thread, they are actually dynamically allocated as well. So what this means is that thread memory, whether it be a split stack from like a Go thread or your traditional POSIX thread, they all belong to dynamic memory. This is very interesting because on a Linux machine, which is where I dump this, I can now identify what parts of my process memory space are threads. Okay. So I've trimmed out some of the output here, but I've highlighted there at the bottom part where the thread belongs. You can see that it is not assigned to any object file there on the right column. It's just an empty slot, and there's read and write permissions on it. Before that wasn't there, but then when I started allocating threads, you'll notice that these additional pages keep just growing, so my process gets larger and larger. So I can look at any memory space and find potential pages of memory where a thread lives. Now remember, threads have stacks, stacks have return addresses. So now this is narrowing my search to try to attack a return address of a running process. So we're going to have a little bit of fun. All right, it's my boy Alex there. And so what's that, the bottom question mark there? It looks very similar to what I just showed there. That's probably a thread. Maybe not, but we can make a rough, make an assumption here. I'm not going to ask you guys what the answers are here. Probably a thread or stack area for a thread there. But what about the other one? The other page there, the one right above it. That's kind of interesting. Notice the permissions on it. There are none. There's no read, write, or execute. It's just dash, dash, dash. Well, that's what's called a guard page. Basically, if you do mprotect and you protect a page with the protect none flag, it sets absolutely no permissions, and if anything reads or writes to that page of memory, your program terminates because it throws an exception. The CPU says there is a segmentation fault. That's a security mechanism, so that if you're overwriting pages or you're scanning memory or trying to touch that, the program will just immediately terminate. Okay, so as I've hopefully convinced you all now that stacks are obviously critical pieces of information. They control the flow of a program because return addresses live on the stack. So of course it makes a lot of sense to protect the stack, right? Well, there's a concept called a stack canary. This is, ancient technologies, but the idea is you place a known word, you being the compiler, when it creates the program, it places a known word at the top of the stack right as the function starts, and then when the function completes, it checks the stack to see if that same value is there. If the value has changed at all, then the stack is assumed to be compromised and the program is immediately terminated. So here's a little more information. Like I said, I'll share the slides later. But here's what a canary looks like, the assembly of a canary looks like. So here's the function foo. I've compiled it using GCC's stack protection mechanism. And you can see right here, and this is going to be fun. All right. You can see right here, there's a little bit of additional information. If I were to compare this slide to the ones I showed previously, you'll notice that there's a few extra instructions. I'm reaching into the TLS or the thread memory for this, this process, and I'm putting some value into the RAX, and I'm moving RAX to 8 bytes offset of the stack. What's in this area right here is the actual canary value. So the canary changes every time you start the program, but it should stay the same during the program. The reason is, if I were an attacker and I knew what the canary value was a priori, then I could write my malware to actually just use that canary. The solution is to use a random word instead. That's what GNU does. So when GNU, or if you're running Linux, a random word will be generated in the kernel, passed all the way up to user land. Your program is launched, and that random value is the canary that is stored here. So if I were writing malware, I have no idea what to actually use as a canary value if I were trying to compromise the stack. Just one lovely little little way that GNU tries to keep things safe. And then right here is the epilogue of the function, and it checks the stack canary set there. You can see it's putting that value into RDX and checking it. If the value changes, then the program terminates. All right. Okay. So that's Stack Canaries, and that code there at the bottom was ripped straight from the kernel, Linux kernel, and that is what it's using to generate the canaries. You can see it's just using the random device on your CPU or on your system to actually generate some entropy and then store it and pass it up to user land. This all is actually used as part of the auxiliary part of an ELF file or of your executable. So now the question comes, can a canary of maximum entropy used to find addresses in an opaque memory space? Well, yes, of course it can. That's the band yes, if you didn't get the joke. Nobody laughed. Wow. At least I'm not a comedian, because that would suck. All right, so this is Klaus Shannon, the man who coined the term, well, he didn't coin the term entropy, but he tried to measure entropy. And his definition is, it's just the average amount of information given an event. So what we're trying to do is look into memory space, look for the highest entropy word, because I'm pretty sure that's going to be the canary. And then I know that the canary value lives a certain way from a certain distance from the return address. So all this means is I scan a memory, or you can scan a memory dump, look for the highest entropy word, and then know that 16 bytes from that is going to be where the return address lives. If it's not, well, you might break a program or two. Who cares? There's false positives. It's not a perfect science here, but it does work. I thought he looked cooler with the glass. No, he looks cooler without the glasses. Like, seriously, this guy's awesome. So I just kind of define, my concept of maximum entropy is based off of Shannon's entropy. It's not entirely, it's not a total, it's not total, but it is very close. And what I do is I look at a word size, an address size, and I look for any address or any value where every byte is a different value. And that's what I call maximum entropy. I'm not looking at the bits, I'm looking at every byte, just seeing if there's in the word, if every byte is different, I call it maximum entropy. And that seems to work. So how frequently does this occur on a system? If it happens all the time, then I'll have a lot of false positives. So I scanned my entire system. It took a long time, but I was drinking coffee. And I don't really care. And it actually turns out it's actually pretty rare. Look at that. I mean, I'm not going to read the slides to you, but this doesn't mean a lot. Let's draw pictures. So here's I decided to write a heat map instead of the highest entropy words. Now, if you're colorblind, I deeply apologize. This is going to not make any sense. But the red items there, I think there's 4 diagonal in the middle, 5, 6, 7. I see 7 red items out of this entire memory space. I removed all the 0 bytes because this would have been enormous otherwise. But this is looking at just one single process. So as you can see, the highest entropy words are pretty rare. So this leads to the attack where you scan the memory area of a process, you look for the highest entropy word, and then you look for a value 16 bytes from it, because that's probably a return address. If that value is in fact a value that lives within the memory space, if it looks like an address and it smells like an address, it's probably an address. So there's a little bit of duck logic there, or platypus logic. And it actually turns to work. So that's basically the hack there. Is quite simple. Using the security mechanism provided by a Stack Canary, we can now identify return addresses. So I've got a lot of information here. I'll post the code I have written, which I haven't posted yet because this is going to be really cool. It's going to do like a live, like I'm releasing now. But I'll just do it later. No big deal. and you can look at it, you can make comments. You've got my email address, it's at the top, so feel free to hit me up with any questions.